Welcome, welcome. My name is Barry Bolding, and I lead worldwide high-performance computing at AWS, which for AWS, we actually call my team the HPC Plus team, because we look at high-performance computing as a holistic set of advanced solutions, advanced simulation problems. And today I'd like to talk to you a little bit about that high-level view and some of the trends we're seeing in high-performance computing, and specifically how they will play into some of the manufacturing and aerospace industries. And today I also have with me Colin Haubrich, and Colin is the head of IT at Wisk Aero, and he's going to talk to you a little bit about how Wisk is using AWS to solve their aerospace problems. HPC today impacts every part of our lives, and whether that's the coffee you drink every morning and the design that goes into that coffee maker, the glass break simulations, it's the phones that you carry and the drop testing that's done on those. It's the weather modeling that's behind you looking and seeing if it's going to rain or snow tomorrow. Behind every one of those is a set of applications and simulations that are driving the advancement of our society. And when we look at HPC at AWS, we look at workloads. And those workloads span across multiple domains and verticals. And they have different characteristics. It used to be, traditionally, you would look at high-performance computing and you'd ask basically two questions. Is it a tightly coupled workload or is it a loosely coupled workload? And that was kind of the bifurcation tree, the decision tree that you would use to decide what software and hardware you would be using to solve your problem. And those are two very important criteria. An example of a loosely coupled methodology is financial risk analytics, where you have thousands or millions of simulations that are calculating the risk on a financial portfolio. And a financial company will then, at the end of the day, based on their current ownership and profile of stock, formulate a risk for the different portfolios that they have. A tightly coupled workload is something like computational fluid dynamics or weather modeling, where you have a large problem and you're distributing that one problem across multiple compute instances. And in that type of a simulation, it's very important to have a physical locality. It's very important to have messages moving between the different instances as the simulation is progressing. But even more importantly, over the last 3 or 4 years has been an additional question that needs to be asked for many of these workloads. And that additional question is, are you going to use machine learning in your workflow to help advance or accelerate that simulation? And more, this is becoming a stakeholder question in every conversation with customers, whether that's an aerospace company, whether that's a energy company, whether that's a national laboratory doing advanced research. And so I think of this as a convergence that is accelerating HPC. And the convergence of machine learning and traditional core HPC takes several dimensions or characteristics. It can be acceleration through the algorithms. So it is that ability to use a training mechanism to pre-process or pre-validate some of the simulations that you're about to do. If you're a drug company, you may want to do, as Adam talked about in his keynote, look at billions of drug candidate molecules, screen those drug molecules, and then advance that pipeline to a more accurate simulation that you can do. So that acceleration of workflows through algorithms is critically important today. There's also acceleration through technology, and the acceleration of being able to access the latest large memory, accelerated compute GPU, accelerated training technology or inference technology, the ability of a workflow to access those technologies that they become available means that you're not locking into an HPC algorithm for 20 years. And I will say, as someone who's been doing this for all of my adult life in the supercomputing domain, there are many applications out there that have locked in an algorithm, and they're still using the same designs for that software algorithm that they were using 30 years ago. And sometimes there's a good reason for that. If you're a national laboratory doing nuclear stockpile remediation, you need to validate and make sure the simulation gives you the same results, the accurate results that have been validated and tested over time. The same is true if you're in the healthcare industry and you're doing simulations that relate to clinical and drug design. You need to be able to provide regulators that data. So, but at the end of the day, if we're locked into those technologies and those algorithms, we're going to just slow down our pipelines. So we got to be really thinking in an innovative way. And then finally, as I said, at the base of this is acceleration through parallelism. This was the foundation back when I was at Cray Research and at IBM, when we were first using application methodologies such as parallel virtual machine and MPI to parallelize applications. This was a groundbreaker. It fundamentally changed the type and size of problem that we could solve. And that parallelism has become so ingrained in everything we do. It really did change the way that we look at design. But I will say, over the last 4 or 5 years, this advent of convergence of machine learning into the algorithm, I'm seeing that same step function change in the acceleration of workloads. And I see this as the domain. Just as we got researchers together back in my day at Cray Research, we had these workshops where we would bring all these companies together and we do a workshop on parallelism using PVM or MPI, and the researchers had never ever thought of parallel applications. Today, the same is true. We're bringing together researchers and we're into workshops where we're talking about machine learning and how that can advance your HPC simulation. This spans workloads. As I said, my teams at AWS and the way AWS looks at high-performance computing is in a horizontal fashion, because many of the learnings in a converged world where you're using machine learning and HPC, you can take those learnings from one domain, one vertical segment, and transpose those into another domain or vertical segment. And we're seeing today exactly that. Training and simulation 5 years ago for autonomous vehicles changed the game. They had a workflow that brought in data from cars, did training on those algorithms, piped those into a simulation where they're doing road driving simulation, and that workflow is now standardized into those autonomous vehicle companies. And now that's a similar workflow, at least in paradigm, to some of the drug discovery applications that are going into things like OpenFold with virtual flow, where you're doing either drug screening or where you're doing drug prediction or protein structure prediction, where you're doing a combination of machine learning and classical simulations. And so we have all of these. And in fact, there were announcements over the course of reInvent in many of these domains. One of the most exciting ones that my team works on is the SimSpace Weaver. I don't know if you saw that application where we're simulating 1 million entities in Las Vegas, walking around. And those crowd simulations, that's large-scale HPC. That's simulation at scale. And again, you're going to need to couple those simulations with machine learning, behavioral, living digital twins. This is all going to come together to give us new ways to innovate, research, and find solutions for the cutting-edge problems that we face. Finally, cloud gives you scale. And if you're going to really accelerate the work that you have to be unbound from the dimensionality of an on-premise system. And that scale that AWS gives you is really a game changer. In fact, the virtual flow work, this week we had presentations going up to 5.7 million vCPUs, using virtual flow, and using the research work at Dana-Farber and Harvard that was in Adam's keynote. So I really recommend you watch that keynote, or you watch the researcher actually gave a panel discussion here at reInvent, and you can watch that online. So I'd really recommend you go find those and look those up. Now, why AWS? Well, as someone who has been in the supercomputing business for many years, it's really critical that we build the trust and build the momentum of technologies and innovations that give you confidence that AWS is the place to get your work done. And over the last 5 years, we've really had this rolling thunder of services and applications that we have released to our customers that give us the set of base technologies you need to solve these problems. Because if you're going to have that coupled workflow of machine learning and HPC, you're going to need good training devices, good technologies, all of those profiles that I showed you in the triangle of technology include software, storage, networking, and compute. I should say, on that chart, several announcements this week: HPC 7G, our Graviton ARM-based compute instances, HPC 6ID, which is great for finite element modeling and mesh modeling, using applications such as Abacus and PAMCrash. Of course, we already had the HPC 6A, which is fantastic for computational fluid dynamics, and I think something that Colin's going to talk about. You can also look at these technologies not just in terms of when they came out, but in terms of what problems they solve in your ecosystem. And so we need to make sure we have great compute, great networking. We also announced here at the show EFA Gen 2, and EFA Gen 2 is really showing that we're dedicated to giving you that tightly coupled, high bandwidth network that you can do either MPI-based applications or that you can do distributed training on. A few weeks ago, a few months ago, we announced FSx on tap to complement our FSx for Lustre. We also announced FSx file cache that allows for caching of data from on-premise and into the cloud. And then in the batch domain, in the orchestration of jobs, a couple of weeks ago at Kubeflow, we announced AWS Batch on Kubernetes, which, if you'd told me 5 years ago when I was at Cray that your conversations with customers would be about Kubernetes for their HPC applications, I would have kind of given you a strange look. But more and more HPC customers are using solutions like Kubernetes to orchestrate their work and containerize their work. So I've given you the overview of HPC and HPC+. I want to talk to you about a particular set of innovations that can exemplify what's happening. So in HPC+, especially for engineering, it's used everywhere in terms of crash simulations, drop testing, aerodynamics, thermal cooling, engine design, prolonging the life of batteries. These are all applications that have HPC underneath them. Examples of customers we've worked with, in addition to Wisk, who's here with us today, Commonwealth Fusion, where we're doing basic physics combined with their containerized solutions using batch to do particle transport and multiphysics. We have aerospace companies pushing the boundary of turbulent flow with supersonic transport. And then finally, I mentioned drug therapeutics. AWS played a critical role in many of the vaccines that came out to treat COVID, and we have great partners in that space doing groundbreaking discovery every day. In terms of HPC+, as it pertains to prediction, there's what I would call core HPC of computational fluid dynamics. Today, there's also on the other side the predictive digital twins, the predictive simulations. That's the SimSpace Weaver that I mentioned. In the middle of it, today I'm going to talk about accelerating a CFD workload with machine learning and some of the innovations that have happened there. So it traditionally takes dozens of hours to do an HPC simulation, and It could take even days if you're doing a highly accurate simulation. Say you change a bumper on a car, or you change an airfoil, or you change a blade design on a turbine. And then you rerun that application to get an accurate CFD. And then so the engineer submits the job, they go get their coffee, they go home for the evening, they go home for the weekend, and they come back, and then okay, the results come back, maybe it worked, maybe it didn't. They redesign, they tweak it, they resubmit another job, and there's a serial workflow process there that is inherently slowing down and inhibiting the design process. So if you can enable the researcher to literally change the design and get the CFD solution back over a minute, you would jump at the chance to do that. And so there is a set of what we call physics-informed neural nets, is a methodology that has evolved very quickly. So the seminal paper for physics-informed neural nets came out in 2018. And here we are, almost 2023, 5 years later, and physics-informed neural nets are literally everywhere, in every conversation I have with engineering companies especially. Is it used in production yet? It's still being tested, I would say. But there are direct applications that are working very well. There are also applications that are not working so well, where the methodology is too complex. But the idea is you have intrinsic physical equations that govern your simulation. And traditionally, you just broke those down, you wrote a program, and you solved the partial differential equations associated with that. In a physics-informed neural net, oh yes, I kind of get a little out of sync. These are some of the papers that have come out over the last few years. And what folks have done is they've begun to package these up to make them available for researchers and for commercial companies and people doing actual production work to get access to those neural net scientific libraries and actually begin to use these on a daily basis. So then now let's kind of look at why this is really important if you're doing that design. If you have experimental or simulation data that's highly accurate, and you simply do a training model against that data, you can only fit the data and interpolate between the data points. You actually can't really extrapolate very well from that data. And so that's just a fundamental design of the neural net. And so, maybe you deepen the neural net, maybe you do a large language model, maybe you do a transformer model, but at the end of the day, you're going to be somewhat limited to interpolation. In a physics-informed neural net, what you basically do is you weight the loss function that you're doing your training against. And you weight that loss function with the actual physics equations that you're using that govern the equations of motion. So in this case, basically a damped harmonic oscillator, you weight the loss function, you retrain the neural net, and essentially the neural net now can, with sufficient training, basically replicate the physics that you're seeing. So you get a trained model. Well, inference against a trained model is almost instantaneous. So now I can actually have a design parameter for a bumper, and I can say objective 1, I want the lift on the front of the car to be X, and I want the drag on the car that's following me to be Y. And I have 2 parameters. And I'm going to train a very accurate physics model. Then I'm going to start changing bumpers, and I'm going to change designs on the cars. And I'm going to look at, as I start changing these, I'm going to extract by inference the coefficients of those 2 parameters that I want to gauge my design against. And I can run through 10,000 car designs in a matter of minutes, select car designs that give me the qualities I like, and look at them. They may make sense, they might not make sense, it's just a trained model. Hopefully they make sense. Then I do a very accurate physics simulation against a design that I have confidence in. That acceleration of the design is really going to be groundbreaking for, changing the airplane, the tips on airplane wings to get maximum fuel efficiency, to changing the designs of turbines within dams and hydroelectric energy-producing devices, wind turbines. All of these you can now run through hundreds and thousands of design parameters. There's an example that didn't work so well. We were working with a company that wanted to look at plastics molding flow. And so they said, hey, let's do a POC. Let's test whether we can do injection molding of plastics, and we can do some accurate simulations, and we have some structural design of the device we're trying to create through the plastics molding. And then we will change the designs and see if we get accurate, reproducible results. In this case, we didn't. And the reason is plastics molding is both a physical flow problem and it's a cooling thermal problem. And they're coupled. And so training a model, it's not that this won't work, it's just that there's got to be some researchers out there who go off and spend some money doing some work on what are the best loss functions to use if you're going to train a model to do both a coupled thermal and fluid flow problem. So this is really a domain that I am very excited about. I'm just excited to see how machine learning and physics are going to work together to solve these massive problems. So at this point, what I would like to do is have Colin come up and tell you about some of the really amazing work that Wisk is doing.
Great, thanks, Barry. So once again, my name's Colin Halbrecht. I'm head of IT at Wisk Aero. And I'm going to play a little video here for you. So this is our Generation 5 aircraft. And for those of you that are not familiar with Wisk Aero, we're actually designing an autonomous air taxi. We just launched our Generation 6, or announced our Generation 6 about a month ago, which will be the one that we take to FAA certification, and it's going to carry 4 passengers and take you from places in the urban area, from an airport maybe to downtown in 10, 15 minutes without a pilot. Oh, video. Sorry, there we go. So you can see it flying here. There's a little shot of the airplane flying. This is actually an autonomous flight that our Generation 5 aircraft is doing. Wisk is about 500-person company right now, joint venture between the Boeing company and Kitty Hawk, leaders in the aviation space. We're based in the Bay Area, also with offices in New Zealand, Atlanta, and recently Montreal, Canada. We've actually done over 1,600 test flights, so well more than a lot of test flights. All right, I'm going to go into a little bit now about our HPC environment and why we started looking at AWS. So Wisk has been through various iterations from Kitty Hawk over the last 10 years to now Wisk Aero, which is an independent company with the joint venture. We had an old, archaic compute farm environment, sitting in a data center, about 100 computers that were 7, 8, 9 years old, and that was running our CFD simulation. And it just did not support the designs that we needed to do for our next generation of aircraft. We were also running into power and cooling constraints at our co-location facility. Didn't really want to take down additional co-location facility space and pay the high fees for Bay Area real estate. In addition to that, the team that built this HPC environment was no longer at the company. So we were having to learn how to manage it. It was self-supported in our environment. It was difficult. It was failure prone. I think it went down maybe every other month with issues, and we had to reboot the whole entire cluster. And it just wasn't sustainable as we were going forward. We looked at replacing the entire environment with new hardware and the capital expenditure that would take. But we also asked the question, can we do better? Can we do something in the cloud? And that's when we started looking at AWS and other cloud solutions to see what was possible. We had some very specific goals, though, that we need to adhere to. For one, the software that we run in our cloud is actually supported and provided by NASA and is export controlled. AWS was one of the approved cloud vendors that they would allow us to run the software in. So we were bound a little bit by that. We also need to quickly scale to support our Generation 6 aircraft. Many of you are aware of the supply chain issues that we have right now. If we were to rebuild our data center with the servers and the network switches and everything else that we needed, it could be months before we could get an environment stood up to be able to support a Gen 6 aircraft. We wanted a fault-tolerant and redundant system. We wanted to get out of these regular failures we had in our environment. We also wanted a system that was well supported. We built it, we would know how to build it, but we could document it, and it was a common skill set that we can go out there in the industry and get as we continue to grow. And finally, we're still a startup phase, so we want to minimize our cash outlay and spend the cash as we need it on our design workflows. So the solution that we came up with was that we partnered with a AWS partner at Converge to do a pilot to validate parallel cluster in the AWS GovCloud. This was new territory for us, so we weren't sure how it would work. So AWS and Converge came together and sponsored a pilot for us to test it out, and we were able to get it running. We had to solve for the low latency and high requirements that these CFD tools take, and that was done using the FSX for Lustre file system, as well as the HPC 6A high-performance compute nodes. Part of the problem that we were running on an Intel platform, and we were now moving to AMD. So we had to recompile the CFD tools, Overflow and Fun3D, to actually get to run in the AWS cloud. And we had some challenges in getting those to run initially, but we were able to work through them and got them running. We had all this data set that we had to move into the cloud and make sure that it was cohesive and integral, and that was moving it up into the FSX for Lustre and S3, and make sure that that data sync could happen seamlessly between our environments. And finally, we needed to provide an environment that the engineers can go in and actually see the visualizations afterwards. And that was done using the nice DCV GPU-enabled solution and replicated what we previously had within our data center on-prem. On the left here in the slides, you see kind of our old environment. We had this GPU-empowered workbench. It was a high-powered machine. We had petabyte storage that we had to manage. We had there's a typo there, but it was actually 100 Intel-powered compute nodes in our environment. As we were moving into the AWS cloud, that was done using the parallel cluster, the HPC 6As, and we had the storage that replaced the petabyte storage with the FSX and S3s, and then the presentation layer of the nice DCV and AWS System Manager and SSH keys to access that environment. Our job request goes through a tool chain, submission, the user gets authenticated, the jobs get executed, and then we get the results. This shows you a little bit of the results that we did in our HPC environment as part of the test. So on the top right, that's our vortice magnitude simulation, which is actually testing out the structure of the fans at both high and low speeds. The red is the low speed, and white is the high speed, and it shows you the fan flying towards the left. On the bottom left, this is actually the ground effect of our fans and trying to lift the aircraft on the ground, and it shows you the crossflow of that air on our Generation 5 aircraft. And on the bottom right, that's the turbulence you see on a high-speed descent for the aircraft. And these were all simulated in our solution in AWS. So what did we achieve by moving to AWS? The first thing was scalability. We had a September peak, followed by an October lull. We used half as many nodes in October that we did in September, and we paid for what we needed. We weren't paying this consistent depreciation on hardware in our environment. We got about a 30% runtime improvement by running in the AMD and the newer servers. But more importantly, we got a 50% plus job turnaround time improvement. And this was really bound by how many HPC 6A nodes we wanted to put at the solution, right? So we came up with a number that we wanted. What's a reasonable turnaround time? The week plus with the old solution was not great, but the 50% is a few days now to get results back or even sooner. The biggest win here, in my opinion, is the supportability. We're now supported by our partner Converge, so when we have issues, we can reach out to them. They are there. They meet with us weekly. They're really helping to make sure our environment is running well. We have built-in knowledge within the current IT team of our new solution now. And we have the enterprise support and backing of AWS and Converge. Our old solution was kind of in-house built. We had to figure out whenever stuff failed, how to fix it. And sometimes it can be down for 2 days, 3 days. The new solution, we haven't had any outages since we went live. We're in a secure environment now. We had to set it up in AWS GovCloud, but that's secure. So I feel confident knowing that my data and my work is being done in the AWS GovCloud. We've integrated it with Okta, with MFA for user access. And we have defined roles and ownership within the teams, both on the engineering side and on the IT side that's supporting it. We're also getting real-time visibility. We can go in at any time and see what our dollar consumed is on a regular basis. And we do a monthly metrics review of how much have we used, what's our prediction looking like for the next month. And it's allowing us to manage our cash and cost a lot better. As we look out to the future, CFD was just a starting point for us in AWS. It was the first time Wisk has used AWS for any type of workload scenario. As we look out to the future, we're an autonomous flying taxi. With that, we need to simulate autonomy and flight autonomy and simulation. So we're looking to really build and develop and leverage some of the machine learning models that exist out there to help us model what our flight systems will look like in the future. We're also looking at it as a possibility for hosting some of our business systems and getting those off-prem, off our VMware environment. We're also looking at what we're doing for storage. All our flight test data right now is hosted on a big internal storage environment. Putting that into one place in the cloud, as well as all the other data that we're generating, will allow us to analyze and pull that data by our engineering development team any which way they need it. In their software department, they're still working on kind of old, Linux laptops, developing their stuff kind of holistically. We want to build a standardized development environment for them in the cloud that they can stand up instances they need and do simulations and tests and on the software side. And lastly, we're looking to how we can leverage AWS to better support our opportunities with our partners. Things like Amazon workspaces potentially, or even just having our partners that help us design our aircraft log into our AWS cloud and do simulations and leverage our AWS environment in that way. So overall, we've been very happy with the partnership that AWS has brought to us so far. It's really helped us accelerate some of our design work. And I'll now turn it back to Barry to wrap up, and I'll be available afterwards for questions.
Thank you, Colin. And I want to, it's a great presentation. It really exemplifies the way that our HPC customers are expanding their use of AWS. And the idea that he and his teams can get access to these HPC capabilities at a moment's notice is really important to us. And in fact, you notice as we've branded these HPC instances, there are a couple of characteristics of those HPC branded instances that make them ideal for customers like this. One is that we actually have limits set on those so that HPC customers can use these nodes for tightly coupled workloads. And so Wisk, or any company, they start using it and, they quickly run into limits and we get notified and we make sure they're an HPC customer, that they're using the MPI tightly coupled portion of the design. They're sitting out in the regions like any others, but they're not available on spot, so they're not going to be used kind of as a capacity filler by someone else. They're standing ready for weather simulations every day. Several times a day, weather companies are doing simulations on the HPC instances when they need it, on demand, on a daily basis. Wisk is able to get what they need when they need it and do these MPI-based applications because only HPC customers are using these in volume, and that's what they're designed for. We want HPC customers to have access to these critical technologies. And yet, the design, whatever infrastructure you design to do that run, Wisk can take that design and run it anywhere in the world. And it can run on C6i, or it can run on, it can even be built to run on GPUs if they end up using some of accelerators and some of the software. So the design is capable of running everywhere on any of the EFA-enabled nodes that we have using parallel cluster. So it's really a unique kind of transparency of HPC, a transferability to any of our regions, any of your solutions. It's not a unique technology that you can only pinpoint use in one place. So you're designing for sustainability, you're designing for long-term usage of this software. I want to close Colin mentioned partners right in his closing bullet. And it's one of the important things about AWS is we have a fantastic group of partners we're working with in the HPC space. And I always like to give thanks and kudos to those partners because it's with them that we're building that confidence that we can solve any problem. We have partners both in the ISV space with companies like Ansys and Siemens and Cadence, Synopsys. We have our technology partners such as Intel, NVIDIA, ARM, and AMD. We have our integrating partners. Some teams, some design houses, some design teams are small. They have engineers, they have scientists, but they're not experts at cloud deployment and cloud technology, and that's not an investment that they want to make. And so we have our solutions integrators, Converge or Ronin, Total CAE, Rescale. And there's enough flexibility and breadth in that set of partners that you can find the one that fits your needs if you need a partner to help you get started and enabled on AWS. Or you can work directly with our teams to help you get started. We have our professional services. We actually have an HPC-specific professional services team that every day deploys these types of architectures for high-performance computing customers. And so I think this is a really valuable resource that everyone should be taking advantage of. We also have a couple of really strategic announcements in the last year that enhance this ability and will try to even simplify the access to HPC software and applications even more. Ansys Gateway, basically on Marketplace, the ability to get access to Ansys solutions and run those straight out of Marketplace. That is a really powerful methodology that many of the software companies are starting to use. Siemens, for their Star CCM, CFD applications, has a very similar strategic alliance with us to create solutions around HPC. So we're working with those key partners to make sure that companies like Wisk are enabled to solve the problems that they need to solve. GovCloud was mentioned, and that's another key resource for many of our HPC applications. Now, one thing that Colin mentioned was he had to do some recompilation, he maybe had to do some tweaking because he was moving from one technology to another. We also have partnerships with entities like Lawrence Livermore National Laboratories, where we recently became the host for the SPAC repository. And so SPAC allows the deposit of applications built specifically for different technologies. So if you need overflow or if you need GROMACS, which is a molecular dynamics simulation built for ARM or built for x86, you can go and grab those SPAC repositories, deploy them, download them, deploy them straight into your AWS environment, and they're already pre-built for the base technologies that you're using. So that greatly simplifies that blocker that some people have of having to do their own recompiles of different applications. So we're just continuing to break down these barriers that folks have. So hopefully, we've both given you a view of some of the exciting ways that HPC is evolving and changing and making your life better to solve those big simulation problems you have. I want to thank everyone for powering through reInvent. It's been an exciting week. You can catch us as we're on our way out, and we can continue to answer questions. So thank you so much for powering through. And